Welcome to this lecture where we're going to be looking at the proof of lemma 2.2.5 from our textbook. We've already discussed this lemma in the previous lecture, and now we're going to see how we can prove it. In fact, this lemma relies heavily on the Chinese remainder theorem that we already proved previously. We will see in the proof how we can almost immediately get the lemma from the Chinese remainder theorem. In the lemma, you will notice some of the familiar objects, but perhaps the concept of bijection is something that we want to recall, since this is probably the first time in our course that we encountered this concept. When you have two sets, let's say x and y, a function f between them is said to be bijective when it has the following two properties. Firstly, for every x1 and x2, if f of x1 equals f of x2, then x1 equals x2. This property is called injectivity of the function. There is another way to phrase the same property by logical process called contrapositive. If x1 is not equal to x2, then f of x1 is not equal to f of x2. And this must hold for all x1 and x2 in the domain of the function. Let me indicate that here. So the x1 and x2 come from the domain of the function, in which case, in this case, it is x, right? Why are these two properties the same? Well, in both cases, they say that distinct elements of x map to distinct elements in y. The first one says that should two elements of x happen to map to the same object in y, then they must be the same. It's indeed a way to ensure that two distinct ones will not map to the same, right? Which is exactly what the second one says, that if two elements are distinct, then their values will also be distinct when we apply the function. Okay, so that's injectivity of the function, and then there is a second component to surjectivity, which to bijectivity, which is called surjectivity, which says that for every y in y, there exists an x in x, such that y equals f of x. If we draw a picture for the function, let's say we've got 4 elements in the domain x. The property of injectivity ensures that the different elements, the 4 different elements, map to 4 different elements. You cannot have something like this, for instance, because then you will have x1 and x2 right here, which happen to be different, but they map to the same place, which is impossible by this implication. So the fourth one will also have to map to a separate fourth element in the set y. But injectivity could still allow some elements in y to exist that are not mapped to from any element in x. And that's what the second property, surjectivity, rules out. So by surjectivity, any element we pick in y must have something in x that maps to it. So none of them will be left unmapped. So basically, in our previous picture, we couldn't have any further elements in y that do not come from the set x. As you can see from this diagram, the two together, injectivity and surjectivity, ensure that the two sets have the same number of elements. Of course, when the sets are finite, we know what this means, but we can have also infinite sets, x and y, and then we can't necessarily count elements in an infinite set, at least not with natural numbers. But then still the concept of bijection is useful there, because then with that concept we can still track when two infinite sets have the same size or not. All right, so this is just recalling the concept of bijection, which you might have already seen before. So it's a combination of injectivity and surjectivity. So the two properties together define when a function is bijective. And as such, to prove that a certain function is bijective, we will be proving these two properties individually, injectivity and surjectivity. So let me clean up the space here a little bit. Now we're going to get started with a proof. In light of the remark that I made about the number of elements in x and y when we have a bijection between them, basically what this lemma is telling us is that these two sets are of the same size. In our case, both of them are finite sets indeed, and so the existence of a bijection between them ensures that these finite sets have the same number of elements. Of course, the lemma gives a very specific way of building this one-to-one correspondence. Another name for a bijection is one-to-one correspondence. As you see in this picture, we've got a one-to-one correspondence. Individual elements mapped to individual ones in such a way that no two on the left correspond to the same on the right, and no two on the right correspond to the same on the left. All right, let's get started with the proof. So the first line of the proof tells us that we are going to first show that the function defined here, the function psi, is injective. We are going to use not this formulation of injectivity, but the other one that we had before. We're going to assume that psi of c is equal to psi of c prime, and then try to conclude from there that c and c prime are equal to each other. So if psi of c is equal to psi of c prime, then this means that m divides their difference as well as n divides their difference. Why is that? What is psi of c? Psi of c is given here to be, okay, I think at this point I'm going to take this off from the screen entirely. So what is psi of c? By the definition, as you can see here, psi of c is the ordered pair c modulo m, and let me write it this way, because this notation now refers to the equivalence class of c under the congruence of modulo m. And here we have congruence modulo n, which is another way to write what we intended to put here. So that's what psi of c is. And what about psi of c prime? Well, it's the same formula, so it will be similarly the ordered pair consisting of equivalence class of C prime and under the M congruence and equivalence class of C prime under the N congruence. Recall that the values of psi, as you can see from this diagram, they live inside this Cartesian product, and elements of a Cartesian product are ordered pairs of an element in here and an element in there. And also recall that the elements that go in these start versions of modular numbers are those that are coprime to M and N respectively. Okay, so if it happens so that psi of C equals psi of C prime, this means that the ordered pairs are equal, right? So this ordered pair equals the other one. And then that gives that each coordinates of the ordered pair are respectively equal to each other. So this must be equal to that, and the other one must be equal to the other one. An ordered pair is a pair of objects that is ordered. First position, second position is assigned to them. And so if two ordered pairs are equal, it means that the entries in the first position are the same, entries in the second position are the same as well. This is something very familiar to you, of course, because when we talk about equality of 2 points on the Cartesian plane, in terms of their coordinates, 2 points will be the same when they have the same x coordinate and the same y coordinate. So you can think of this as the x coordinate, and that one is the y coordinate. So because the ordered pairs are equal, we can conclude from here that the equivalence class of C under the M congruence is equal to the equivalence class of C prime under the M congruence. And similarly, the equivalence class of C under the N congruence is equal to the equivalence class of C prime under the N congruence. Okay. Now, of course, this gives us that C and C prime are same modulo M, right? So C is the same as C prime modulo M, and also C and C prime are the same modulo N. And that in turn gives us that C minus C prime is the same as 0 modulo M, and C minus C prime is also the same as 0 modulo N, which in turn gives us that M divides C minus C prime, and N divides C minus C prime. And that's exactly what we were claiming here. You see, we were claiming that if psi of C equals psi of C prime, then M must divide C minus C prime, and N must divide C minus C prime as well. So we're now in agreement with the author of this proof that these divisions must hold, right? Divisibility relations, rather, must hold. Okay. The next conclusion that the author draws from these divisibility relations is that the product of N and M also divides C minus C prime. Let's try to explore why that would be the case. And let me clean up the space here. In fact, we've seen something like this before already. So let me write this out first. So because M divides C minus C prime, and because N divides C minus C prime, the claim is that from this it follows that N times M will divide C minus C prime. That heavily relies on the fact that the GCD of N and M is 1. Now, the way the fact that the GCD of N and M is 1 is useful to obtain this implication is the following. We know that every number decomposes uniquely into its prime factors, right? So think of decomposing m into its prime factors, n into its prime factors, as well as c minus c prime. The fact that m divides c minus c prime means that every prime factor of m is also encountered in the prime decomposition of c minus c prime as many times as it is encountered in m. And the same holds for n. But because n and m have GCD1, all the prime factors of m are distinct from the prime factors of n. So they have different prime factors. But then their product will have prime factors of m together with prime factors of n, and none of them will coincide among each other, right? So all the prime factors of m will be prime factors of nm, and then also all the prime factors of n will be those of nm. But in order for this divisibility to hold, we need to be able to find every prime factor of nm to be also a prime factor of c minus c prime. And we know we can do that because individually on the m side and the n side, this already happens thanks to these divisibility relations. So it is actually, it is important here that GCD is 1, because if it wasn't so, let's say take m and n to be 2. 2 divides 2, 2 divides 2. It does not imply that 2 times 2 divides 2. So what fails, the implication here is that m and n have a common prime factor, while each of them can be found in the prime factor decomposition of the 2 on the right-hand side. When we multiply m and n, they build up together to give 2 copies of that prime factor, right? But the right-hand side only had 1 copy of it, so it cannot accommodate 2 copies. But when n and m are coprime, when GCD of n and m is equal to 1, this will never happen. There will be never a prime factor of this that's also repeated as a prime factor here, so that they don't blow up in the product. Hope that makes sense. Okay, we have actually encountered this fact already before. In fact, in the previous lecture, I remember that we used this fact already, I think when we were proving theorem 2.2.2. But I thought I would explain this here once again, in case some of you didn't catch the reason why this should hold. Great. So we've now progressed far. We've managed to convince ourselves that if psi of c equals psi of c prime, then it must be so that m divides the difference between c and c prime. Also, n divides the difference. And then because GCD of n and m is 1, we can then conclude, as we just now explained, that n times m divides c minus c prime as well. Great. Let's see where we can go from here. Okay, so it seems like we're concluding now that c and c prime actually must be equal to each other in this set. Why is that so? Well, if n times m divides c minus c prime, that means that c equals c prime modulo n times m, right? So their equivalence classes for the modulo nm congruence, for the equivalence relation created by the modulo nm relation, the equivalence classes of c and c prime must be equal. And that's exactly what it means for 2 things to be equal here, because this set is the set of such equivalence classes. Not all of them. We only consider there those c's which are coprime with mn because of the star there. But that part is irrelevant. We still have that. I mean, we don't need that fact to know that these two elements are equal. We don't need the fact that C and C prime come from the star. Okay. So we've now managed to prove that psi is injective. Let's recap how we did that. We start by assuming that we've got two elements, C and C prime. In fact, they're equivalence classes. So we have two elements, C and C prime. They're equivalence classes under the Mn modular relation, C and C prime. And then we map each of them, we map them by psi. When we map them by psi, we get, in the first case, we get the order pair equivalence class of C for the M relation and equivalence class of C for the N relation. And the second one gives the order pair equivalence class of C prime for the M relation and equivalence class of C prime for the N relation. We assume these are equal to each other. We are proving injectivity, right? So mapping two things to the same spot should force them to be the same as well. So we assume they're equal, and that would mean that they're equal coordinate-wise, right? And that we saw can be used to derive that n times m divides C minus C prime, which is another way of saying that these equivalence classes are also equal, which is exactly what we want to show that psi is injective. Great. So we're done with the proof of injectivity of psi. Now let's see how we can prove surjectivity of psi. For surjectivity, we need to pick an element here and show that no matter what element we pick in this set, there will always be something in the other set that maps to that element. Recall that when we have a function f from x to y, it's surjective when for every y in y, there exists an x in x such that f of x equals y. So to prove that this holds, we have to take a random y and prove that there exists an x for it such that f of x equals that y. And this is what is reiterated here. Next, we show that psi is surjective. In other words, that every element of that Cartesian product is of the form phi of c for some c, right? So a random element of the Cartesian product will have the shape equivalence class of, let's say, A under the M relation, equivalence class of B under the N relation. And so that's the Y. That's the random Y. A random Y will have that form. And then we want to show that we can find an X, which we will write as equivalence class of C under the Mn relation that maps to that Y. And mapping to that Y means that when we apply psi to X, in other words, when we apply psi to the equivalence class of C, in other words, when we consider the order pair C modulo M, so the equivalence class of C under M and the equivalence class of C under N, that ordered pair, this one, has to coincide with that one, right? It needs to equal our Y. So let's write down what this means more explicitly. Basically, we're looking for a value of C, right, such that the equivalence class of C modulo M will be the same as that of A. So such that C is the same as A modulo M, and such that C in the second coordinate, this being equal to that, means that C is the same as D modulo N. So F being surjective means that no matter what A and B we pick, as long as we pick them from these star worlds. So A must be co-prime to M and B must be co-prime to N. We will be able to find a C that solves this system of congruencies. But that's exactly what theorem 2.2.2 established, isn't it? It said that, in fact, even if A and B was arbitrary, this would be so. So A and B do not have to be co-prime with M and N respectively. Even for arbitrary A and B, as long as N and M are co-prime with each other, and they are, because in this theorem, in this lemma as well, we require them to be co-prime with each other, there always exists an X that's congruent to A modulo M and to B modulo N. That's what theorem 2.2.2 was saying. So we already know that such C exists just by that theorem. Okay, good. If such C exists, then we can take as our X in the proof of surjectivity, we can take as our X to be the equivalence class of C for the Mn relation. And then when we apply psi to X, we will indeed get the Y we desire to get. So we will have Fx equals Y situation because C and A are the same modulo M. So the first coordinate of the psi value will match with the first coordinate of Y. And since C and B are the same as modulo N, the second coordinate of the psi value will match with the second coordinate of the of Y. That's what I explained here as well in the proof. Given A and B with GCD of AM equals 1 and GCD of Bn equals 1, even though we don't need that part, theorem 2.2.2 implies that there exists C such that that holds and that holds, and then we're done, because that's what we were looking for, right? We were looking for a suitable C. There is an additional remark that's made here that we may assume that the C, in fact, is between 1 and n times m. And we're going to now unpack why that is true. In fact, we need to have determined that already when we were building the psi function. Let's talk a little bit about that. So I'm going to now explain what this remark here of forcing C to be necessarily between 1 and m has to do with ability to define the psi function in a valid way. So it all depends on actually how we view the elements of these sets. One approach is to say that Z over mnz star simply consists of all the integers, let's say x, that are bigger or equal to, is it 1 or 0? That are bigger or equal to 1, and such that the GCD, and less or equal to m times n, and the GCD of x and mn is 1. So this is one way of thinking of the set. But another way of thinking about it, okay, before I explain what is the other way of thinking about it, so if we think of the set that way, right, then you see that we do want this C value, which must be in the set, to be between 1 and mn. That's why the author is trying to ensure that we do have such C, and we'll explain in a moment why we would. But now another way of viewing the same set is in terms of not the actual representatives of those equivalence classes, but the entire equivalence classes themselves. So the equivalence class of X under the Mn relation, such that GCD of X and mn equals 1. Okay. If we take the second approach, then we have to be a bit careful in how psi is defined, because psi of such an equivalence class, according to our definition, would be the pair equivalence class of x under the M relation and equivalence class of x under the N relation. And once again, on the other side, we can also view these sets in two different ways. One, actual representatives of these equivalence classes, the first one belonging from 1 to M, the second one being from 1 to N, or in terms of the equivalence class themselves. So if we take this other approach where we view these elements of this star construction, we view them in terms of the equivalence classes, then the formula here might give us a trouble. Why? Because you see, the formula seems to depend on the choice of the representative of the equivalence class. We're saying here that psi of this will equal that. But what if we choose a different representative of the same equivalence class? Will the corresponding value according to the formula match with the value here? If it doesn't, then it's a big problem, because then it means that for the same value in the domain of the function, we have two different output values. And a function cannot work like that. A function needs to produce a unique value once the input value is unique. So we do want to ensure that if x and x prime have the same equivalence class for the Mn relation, then these ordered pairs are also the same. And that's actually not difficult to see, thanks to the fact that M and N have GCD of 1. So let's see why this will be so. Imagine that x is the same as x prime modulo Mn. Why would x and x prime be the same as modulo M? Well, if x and x prime are the same modulo Mn, then we can, let's say, write x as some sorry, we can then take okay, which way is the best to approach it? Maybe it's best to approach it through the difference. So we can take the difference between x and x prime, and then we know that Mn will divide the difference, right? Because this would give the fact that x and x prime are the same modulo Mn would give that x minus x prime is the same as 0 modulo Mn, and then that gives that Mn divides x minus x prime. Now, to get that x and x prime are the same modulo M, we want x minus x prime to be divisible by M as well, right? So does this imply that M divides x minus x prime? Well, of course it does, doesn't it? Because M certainly divides Mn, right? So if Mn divides x minus x prime, then certainly M will also divide it, because M divides Mn. And so we can then get that M divides x minus x prime. This is transitivity of the divisibility relation, which then gives that x minus x prime is the same as 0 modulo M. So in fact, we didn't even need the fact that M and N are coprime for this. And that becomes then the same as x being congruent to x prime modulo M. And in exactly the same way, we can establish that also x and x prime will be the same modulo N. Okay, so once we establish that, once we know that we can actually work with these sets, as we have been doing in the past, we can work with them in terms of the entire equivalence classes, and that the function psi is not affected by which representative of the equivalence class we pick. After that, knowing that, we can say that indeed, having found a C such that psi of C equals to the element we fixed on this side when we were proving surjectivity, having found such C, we can then take the equivalence class of that C and then pick another C from the same equivalence class, which will be actually the remainder of the C we found when we divide it by n and m, and so hence ensure that we can also find a C between 1 and m. Okay. But now, how do we know that this C that we found? Remember, we were looking for equivalence class of C in here that would map to a designated element we started with in there, which was actually the ordered pair of equivalence classes of A and N. We were looking for equivalence class of C that maps there. But we found such C. We found a candidate. But we do need to ensure that this object actually falls in the star construction, that it's not just an element of Z over M and Z, but it's actually an element of that star. How do we know that is the case? Well, the explanation that's given here is that because A and B, sorry, this should have been B, right? The second one here should have been B. So because A came from the star and B came from the star, it means that GCD of AM is 1 and GCD of BN is also 1. Right? Why would that imply that GCD of C and M is 1 as well? Let's unpack that one. So let me clear the space here so we can unpack that as well. So where are we in our proof? We started for proving surjectivity of the function psi that goes from Z over Mn Z star to the Cartesian product of Z over Mz star and Z over Nz star. We picked an element AB in there, our Y value, and then we were looking for an X that would map there. We figure that such X does indeed exist. It is given by the equivalence class of C for the Mn relation. In fact, A and B already were in terms of the equivalence classes, so let me rewrite it accordingly. So you see, I keep switching between equivalence classes and their representatives. There we go. So we found the C that maps there. In fact, we even know now that we can pick C to be between 1 and M. But now we need to ensure that this actually does fall in the star construction. We know that the others do, so we know that GCD of A and M is 1. We know that GCD of B and N is 1. And what else do we know? We know that C and A are congruent to each other modulo M. And also C and B are congruent to each other modulo N, sorry. How do we know that? Well, we know that because that's what it means for X to map there, right? The value of X under psi would be, so that this element here would be mapped to, I'm just now repeating what we already discussed, right? It would be mapped to the equivalence class of C under the M relation and the equivalence class of C under the N relation. And knowing that psi maps this element to this, the one we started with, we know that these coordinates are equal. So then C and A have the same equivalence class for the M relation, and C and B also have the same equivalence class for the N relation. So that's how we get this. Now, knowing all of this, we want to be able to conclude from there. So we want to decide whether this implies or not that GCD of C and Mn is also equal to 1. So how can we get that? Any thoughts on that? Feels very it feels like it should be easy, right? It feels like we've seen this before. Let's think a little bit about this. Somehow I've got a mental block now. I don't think I know why this should be so. So let me try to let's try to see if we can prove this on the spot. What would happen if this wasn't the case? What would happen if GCD of C and Mn wasn't equal to 1? It means that we have some number, let's call this number k, that divides both C and also Mn, right? Would we be able to get from here that k must divide A as well? Not sure about that. So k divides C, k divides Mn. That would mean that C equals some Q times K plus R, right? And because C is the same as A modulo M, we can also write C as some Q prime times maybe we can think of it this way. Let's actually think of it this way. So M divides C minus A from here. That can get it from there. And then also we can get that N divides C minus B from there, right? Because okay, so what else can we get there? I'm genuinely stuck now. Maybe it's because 9:30 as I'm recording this video in the evening. I feel like this is the most difficult part of the entire proof, actually. You might want to rewind this a little bit, fast forward. Hopefully, eventually, I can figure out why this is so. I really need your help. Maybe you can actually pause the video and try to figure this out yourself and see if you can actually do it quicker than I. So let's analyze properly all the given data. Okay. So these are, so this is the given data, right? We are given that the GCD of A and M is 1, the GCD of B and N is 1 as well. And we're also given that C and A are the same modulo M, and C and B are the same modulo N. I feel like expressing C in terms of A, and then kind of plugging it in here. So M must divide C minus A, and therefore C minus A must be equal to some K times M, right? For the same reason, and dividing C minus B gives that C minus B must be equal to some L times N, right? That makes C equal Km plus A, and also the same C equals Ln plus B. Now the claim is that the GCD of C and Mn must be 1. So let's say, again, as before, there is some Q, but I've changed the names of variables, but hope that's fine for you. Let's say there is some Q that divides both C, and Q also divides Mn, right? Q dividing C means that Q divides this, right? Q must divide Km plus A, and Q must also divide, because it divides C, it must also divide this. It must divide Ln plus B, right? But because Q divides Mn, we can't really say that Q, because Q divides Mn, we can't really say that Q divides M, right? That we can't say. Maybe we just expand what this means. So Q dividing Km plus A means that Km plus A equals Q times some number. Let's call that number U times Q. And then Q dividing the other one means that Ln plus B equals V times Q, right? So have we taken care of everything here? Q divides C, and it divides Mn. We've expanded what this gives, right? It gives those things. I don't think we've expanded what Q dividing Mn gives. Let's expand it as well. So Mn equals Q times some R, let's say, some R times Q, right? All of these should result in Q being 1. We can't have Q being anything more than 1. That's how we would prove that GCD of C and Mn must be 1. Maybe we can multiply both sides of this by N and both sides of the other by M and see what happens there. KMN plus AN equals UQN, right? The other one gives LNM plus BM equals VQM. Now here we can use the fact that Mn equals RQ. We'll get KRQ plus AN equals UQN. I think we're getting somewhere here. And then also substituting there, we get LRQ plus BM equals VQM, right? And now this equation here gives us that KRQ minus UQN equals AN, right? No, sorry, the other way around. It gives us that AN equals UQN minus KRQ, and BM equals VQM minus LRQ, right? And so AN, so you see that now we're getting that both, okay, so the right hand side of this is divisible by Q and also that, right? So we get that Q divides AN, and also we get that Q divides VM, right? Remember that N and M are co-prime. M and N were originally given to be co-prime. So there's nothing that can divide both. So you see, when Q divides AN, all the prime factors of Q, none of them, wait, some of them could be contributing to N, and some of them could be contributing to M, right? Let's go back and see where we are. So we started off with the assumption that, okay, so first of all, this is the thing that's given, right? We're given that GCD of AM equals 1. We're given that GCD of BN equals 1. And we want to, and we're also given that C and A are the same modulo M, and C and B are the same modulo N. We want to conclude from this that GCD of C and Mn is also 1. Okay. We have unpacked what this means. We've unpacked what this means. We've unpacked it here. I just want to make sure that all the assumptions are being used. If we are not using all the assumptions, we might be missing the ingredients to get to the final conclusion. So we unpacked it here and here. And then that further was unpacked to this and that, right? So knowing these congruences is the equivalent to knowing these equalities. Let's mark them. So this is part of our assumptions, right? Now the third one, that GCD of A and M is 1 and GCD of BN is 1. Have we used that anywhere? Let me see. I don't think we've used that yet, right? I don't think we've used that yet anywhere. That maybe that's what we're missing. Okay. So we seem to have arrived to, okay, so let's see further on how do these assumptions play a role. So we're trying to prove this by contradiction, right? We're trying to find a Q that divides both. Well, not necessarily by contradiction. We took a Q that divides both of them, and we have to show that this Q must be 1. It can't be more than 1, right? So this is also an important part of our assumptions, these two, which then translate to these. Do they? Yeah, just by replacing C with that. So we don't need those anymore. They can be absorbed with this. So we know this is true, and we know that is true. Then what about the fact that Q divides Mn? That's given here. So this is also an important ingredient. And from these, we need to get that Q is equal to 1. Okay, I'm going to write this out separately now. So we have that Q divides Km plus A. We have that Q divides Ln plus B. Actually, we wrote this out as more explicitly, I think, right? We wrote them out here. So we have these 3 ingredients so far, namely that Km plus A equals UQ. That's Q dividing Km plus A. And then we have that Ln plus B equals VQ. That's Q dividing Ln plus B. And then we also have that Mn equals RQ, right? We've got that as well. But we still haven't yet incorporated that GCD of A and M is 1 and GCD of B and N is 1. So let's copy this down. GCD of A and M is 1, and GCD of B and N is 1, right? Okay. And then we started doing some kind of algebraic manipulations, like for example, multiplying both sides by N and M. But we didn't seem to get anywhere from there, right? So maybe we can restart from that spot. Well, we did get to this point. So maybe that's going to be helpful. Oh, I think that will be helpful, actually. Now I'm looking at, so if I combine these with that, maybe that's where we're going to be able to make progress. So let's consider these. From here, can we get that Q must be 1? Take the composition of Q into primes. Let's say Q equals, what shall we call these primes? Have we used the letter P before? We haven't, right? So let's say equals P1 times all the way to P, let's say S, right? These are the primes in the composition of Q. So because Q divides AN, right? Some of these primes will be in the decomposition of A, and some of them will be in prime decomposition of N, and some of them might be in both. But the same primes must also appear in B and M. And we know that we know that N and M are also coprime. That's another thing we know, right? Here, we know that from here. So we know that none of these prime factors of Q can be at the same time in N and M, right? But also none of them can be in A and M because of that, right? So if some prime factor of Q appears inside M, right? But does not appear in, yeah, actually it can't appear inside M, because if it does appear inside M, that same prime factor cannot appear on here, on this side, because no prime factor of A is shared with any prime factor of M, and no prime factor of N is also shared with any prime factor of M. So that prime factor cannot exist, right? So no prime factor of Q can be a prime factor of M. So all prime factors of Q must be prime factors of B. right? But with the same logic, if there is some prime factor of Q that's also a prime factor of B, that prime factor of Q must also be a prime factor of either N or N, or either A or N, right? It can't be of N because B and N do not share any prime factors. So it must be of A. Yeah. So from the fact that from these facts we can derive that Q must divide A and also Q must divide B. Now A and B themselves are not necessarily coprime, right? Or are they? Well, at least we've made some progress. We now know that Q must divide both A and B. How does that help? What else do we know about Q? Let's go back to what we knew about Q from the start. We knew that Q divides, oh, there we go. We also know that Q divides Mn, right? Did we incorporate it somewhere? We did, but maybe we kind of lost it. We also know that about Q. We know about Q as well, that Q divides Mn. And I think that kind of does it because Q divides Mn, right? It means that the prime factors of Q must be either in M or in N. But those prime factors cannot be shared with A, since the GCD of A and M is 1. Yeah. So okay, so let's think about this again. So Q divides A, it divides B as well, right? So it means that all the prime factors of Q are also in A, right? But if they're in A, they can't be in M because A and M have GCD 1. So the fact that Q divides M times N must be at the expense of Q dividing N, right? But then we have the prime factors of Q being shared by B and N as well, which can't happen because GCD of B and N is 1. I think we did it, right? Okay, I'm not going to re-explain everything. You can rewind the movie and see how we got there once again, but we did get there. So we can now see that Q has to be 1. It cannot have any prime factor because that prime factor will be eventually shared by N and B, which is impossible because GCD of B and N is equal to 1. Fantastic. Great. It was quite a shock, to be honest. I did look at the proof before starting to record the movie. I thought that everything was quite clear there. I didn't expect to struggle with this. And maybe I'm forgetting something. Maybe this is something we already proved. I'm not sure now, but in any case, we're now done with that proof. So let me just clear the board here. You might want to write this out neatly in your book, cutting all the unnecessary steps. So the C that we found is the right kind of C, as we have now shown. GCD of C and NM is equal to 1. So the C does indeed belong to that star. Fantastic. This proves surjectivity of psi. Now that we have proved both injectivity and surjectivity, we know that it's bijective. So the number of elements in one set is the same as the number of elements in the other set. That's one of the conclusions we can draw from here. There is a remarkable application that lemma 2.2.5 has. To discuss that application, first we need to introduce this preliminary concept, the concept of a multiplicative function. A function f is said to be multiplicative when whenever you multiply two numbers m and n, when they have GCD of 1, when m and n have GCD of 1, then f times mn equals fm times fn. So that's what we mean by a multiplicative function. We don't mean that it preserves multiplication fully. It only preserves multiplication when the two things we're multiplying, they have GCD of 1. Okay? And using the lemma we just proved, we can establish in a very sweet way, we can establish that our Euler function, remember Euler phi function? That function, the one that counts how many a's you've got from 1 to n, whose GCD with n equals to 1, we can establish that that function is actually multiplicative. And then I will show you why this is useful, why to know that it's multiplicative. It will actually help us compute its values in many cases. So why is the function multiplicative? Well, let's see. The proof says that the map of psi of the previous lemma is a bijection. Sure, that's what the lemma established, right? That this thing is a bijection. Let me actually move this on the right side so we can look at it as we're discussing the other proposition. I hope this is still visible a bit. So we know that this phi is, sorry, we don't know that phi is, but we know that the psi is a bijection. So the set on the left in this situation, this left-hand side set, has the same size as the right-hand side. The number of elements coincide. Right? Okay. But then it follows that this holds. That's strange. Why does it follow that that holds? Well, if you think about it, what is phi of mn? Phi of mn is nothing other than the size of all the a's between 1 and mn whose GCD with mn is 1. But that's exactly the size, that's exactly the cardinality of this star set. The Euler phi function, its value, is actually the size of the star set. And the same goes for phi of m. That's the size of the z over mz star set. And phi of n is similarly the size of z over nz star set. Okay? But now, because the size of the z over mnz star is the same as the size of the Cartesian product of z over mz and z over nz, we know that the size of Cartesian product of two sets is the same as the product of their sizes, right? So we can decompose this into the size of z over mz star times the size of z over nz star, right? So the left-hand side here, the first thing we wrote is our phi of mn, and this one is of course just phi of m times phi of n, and there we go. So by theorem, by lemma 2.2.5, we know that these things are equal. Well, that's exactly saying that the Euler phi function applied to mn is the same as Euler phi function applied to m times Euler phi function applied to n. So we get this remarkable property of the Euler phi function, the multiplicative property. And let's quickly sketch an application of it, how it can be helpful to compute Euler phi functions of other values. So if we take Euler phi function of 4, for example, right, we can write 4 as 2 times 2. But here, we can't use the multiplicative property to say that this is phi of 2 times phi of 2, because 2 and 2 are not coprime. The GCD is not 1. So we can't use it for computing phi of 4. We have to compute phi of 4 from scratch. What is phi of 4? So all the numbers between 1 and 4, whose GCD with 4 is 1. So that will be 1 is such a number, 2 is not, because 2 divides 4, and then 3 is such a number, and 4 is not, because 4 divides 4. So the phi of 4 is equal to 2. Okay. What about phi of 9? Okay, let's see what is phi of 9. Again, we can't use the fact that 9 is equal to 3 times 3. Phi of 9 is, so which numbers are coprime with 9? 1 is coprime with 9. I'm counting with my fingers. 1 is coprime with 9. 2 is coprime with 9. 3 isn't. 4 is. 5 is. 6 isn't. 7 is. 8 is. 7 numbers, right? So 5, 9 is 7. I hope I'm not making a mistake, yeah? But now the remarkable thing is that because of this, now we can say that phi of 4 times 9, which is, what is 4 times 9? 4 times 10 is 40, and minus 9 is, why am I subtracting 9? Minus 4 is 36, right? 4 times 9 is 36. So we now know that phi of 36 must be equal to phi of 4 times phi of 9, because 4 and 9 are coprime, and therefore it must be equal to 2 times 7, which is 14. So we can now get the value of phi of 36 and all the other composite numbers like that, numbers that are powers of primes, by just computing the phi's of these powers of those primes. And so this is a much quicker way of computing phi of 36 than having to list all the numbers between 1 and 36, whose GCD with 36 is going to be 1. So you see, we now have a beautiful application of eventually the dilemma that we proved today, which gave us a bit of hard time towards the end of the proof there. And this concludes the lecture. Thank you very much for listening, and I'm sorry for the little challenge that we encountered there. And actually, I'm not sorry for that. I think it's nice that we encountered that challenge. I hope some of you were motivated to solve the problem, complete the proof before I could do it myself. And if you did it quicker than I, then big congratulations to you. See you next week.